Okay, so the first thing to do here is determine the reactions. So it's a pretty straightforward structure. So what I'm going to start off doing is taking the sum of the forces in the vertical direction. Okay, so let's see, what have we got here? We're going to say the sum of the forces in the y direction equals 0. Upwards forces are positive. What have we got? We've got VA plus VB minus 90 minus 10 acting over 9 meters times a half, all equals 0, and that gives me my first equation, which is VA plus VB equal to 135. Okay, let's just stick a box around that for the time being and park it. Now what I'm going to do is, looking again at the structure, I'm going to take the sum of the moments about point A. Because I know the sum of the moments must equal 0, and one of my unknowns passes through A, which means that equation will yield VB. Okay, so taking the sum of the moments about point A, letting that equal to 0, assuming clockwise moments are positive. What have we got? So we're going to have 90 times the lever arm of 3 meters plus the moment of 50 plus the moment effect of that distributed load, which is going to be 10 times 9 times a half times a lever arm of 8 meters minus 10 times VB must equal 0. That gives me VB equal to 68 kilonewtons. Okay, excellent. And basically I can sub that back into my first equation to get VA equal to 67 kilonewtons. Okay, excellent. Now we can look at this structure again and very quickly recognize there is no horizontal loads applied to the structure, and so no horizontal reaction will be generated at support A. Okay, now we can get on and start thinking about our shear force diagram. Okay, so shear force diagram. So let's just sketch out the structure once again. Okay, so what we're going to do now is from left to right, we're just going to follow the loads across the structure. Okay, so the shear force diagram will increase up to a value of 67 kilonewtons, and that's due to this reaction here. Now there's nothing happening on the structure as we move towards the right, so therefore the shear force stays constant, so there's nothing happening until we hit this point load of 90 kilonewtons. So that's going to cause the shear force diagram to drop down a total value of 90. And that's going to bring it down to a minus 23. Okay, now that's going to continue horizontally with no more loads coming onto the structure until we come across and we hit the start of this 10 kilonewton per meter distributed load. Okay, so now let's go back and rely on something that we learned previously, which was this differential relationship dm dx, or rather we're jumping ahead of ourselves here. Let's go dv, the other relationship, dv dx equal to minus q. Okay, so what's that telling me? Well, that's telling me that the slope of the shear force diagram at a point is equal to the negative of the load intensity at that point, okay, where Q is the load intensity. So let's not worry for the time being about that negative sign, and let's just think about the slope of the shear force diagram being equal to the intensity or the magnitude of the load intensity. Right, so what are we saying here? The load intensity is 10 at this point here at the start of this load, and it drops down to 0. So the load intensity is reducing linearly from 10 to 0 as we move to the right. Now that means that the slope is also reducing linearly. So we're starting off with a large slope, okay, because we have a value of 10 on the left, and that slope is reducing as we move to the right. So the shear force diagram is essentially going to be a curve, and the slope of that curve is going to be a high value at the 10 value, at the 10 point here, and it's going to be, that's point E on our structure, and that slope is going to reduce in magnitude, the slope of the shear force diagram, as we move to the right. So that tells me the shape of this shear force diagram. It's going to be a slope, a larger value of slope, so a steeper slope at the start here, and the slope is going to reduce as the magnitude of this load intensity reduces as we move to the right. And that's going to happen and continue to happen until we hit this 68 kilonewton reaction here, and that's going to induce an abrupt change in the shear force. So the shear force is then going to rise up by an amount equal to the reaction, which was 68 kilonewtons. Okay, so in order to work out what this value up here is, we need to know what the value down here is. So I need to take a shear force value of minus 23 at this point, and I need to take away the magnitude of loading, equal to the area under this part of the loading diagram. Okay, so what am I going to do? I first of all need to know what is the load intensity at that point there. Okay, so that's going to be equal to, you can work this out, it's decreasing linearly from a value of 10 down to a value of 0 over 9 meters. So I can work out that the intensity at that point, okay, the intensity at that point 5 meters across is going to be 10, the value I started with, minus what is essentially the slope of that line, which is 10 over 9, times the distance that I have come across. Okay, let's call that distance x, where x is measured starting at the 10 and moving to the right. Okay, so that's the value. And that value, if you put in x equal to 5, is going to give you 4.44. So I know the load intensity at that point, kilonewtons per meter. So now what I can do is, okay, so that allows me to say that the shear here at this point is going to be minus 23, the value I started with here, minus the amount of force that's represented by this shaded area of the diagram here, which itself is made up of two areas, a rectangle and a triangle. So I've got V equal to minus 23 minus the rectangle portion, which is an area of 4.44 times the length of 5, minus then the triangular portion of loading, which is minus 10 minus 4.44, the height of that triangle, times 5 times a half. Okay, and that is equal to minus 59.1. So I know the shear force at this point is minus 59.1. When I add 68 to that, it brings it up to a value of 8.9. Okay, and then we know that that reduces to a shear force of 0 at the right hand tip of that cantilever, because the shear at the end of the cantilever is 0 as there's no loads applied out there. Okay then, so that's the shear force diagram constructed. That gives us enough information to now go and try and construct a bending moment diagram. We're going to use the expression dm dx equal to v to tell us what the shape of the bending moment diagram should be, and then we can take discrete cuts at different points in the structure to reveal the magnitude of the bending moment at the relevant locations. Okay, so what does that diagram tell me about the bending moment diagram? Okay, so we have a shear force in this region here that has, well, it's a constant value. So the value is constant. That means the slope of the shear force diagram is constant in that region. And so we have an inclined straight line. So that is between A and D. So between A and D, where that's A and that's D, we know our shear force diagram is an inclined straight line. So I'm going to draw the shear, or rather the bending moment diagram, coming down in a straight line down to a point like so. Now I don't know what the magnitude of the bending moment is at that point. I just know that it starts off at 0 here and goes in a straight line to some point down here. Now I know that the underside, by looking at the structure and the loading applied to the structure, I know it's the underside of that structure that will experience tension. And because I draw my bending moment diagrams on the tension face of the structure, I know to draw the line coming down on the underside of the structure, or the tension face. Now, what does this tell me? Here, to the right of D, I have another straight line in my shear force diagram, which means that the bending moment diagram is going to be another inclined straight line, but the slope of the bending moment diagram has changed sign. So between A and D, the slope was a positive number because the shear force was positive, and then to the right of D, between D and E, that slope is going to have changed sign because the shear force has changed sign. So that means that the bending moment diagram is going to come in another straight line, but the slope is going to be the opposite direction. Okay, so from that I know I have a peak here, okay, because the slope here is a positive slope and the slope here is a negative slope. Okay, so now what we have is this curve in the shear force diagram, and that again tells me that the bending moment diagram will also be curved. Okay, so what are we going to do here? So what we're going to say is that between this point, let me just label this up, it makes more sense to have labels. So that is D, E, B, and F. So that was D, that point is E, that point is B, and that point there, the screen stops jumping, is F. Okay, so now between E and B, I know the bending moment diagram is a curve. Okay, so what are we going to do? We're going to continue to curve a bending moment diagram up like so. Okay, so here it's straight. Okay, so that's what that STR is telling me. And then to the right of that dashed line, it's going to curve upwards. Okay, so this is a curve. All right then. Now, so again, the shear force between here to the left of B and the right of B, the shear force changes sign from a negative to a positive. And that tells me the slope of my bending moment diagram also changes. So again, I have another peak. And then to the right of B, I have an inclined straight line, which means that the shear force diagram is still, or the bending moment diagram is still a curve. So I'm going to curve like so down to a value of 50 because I know the magnitude of the moment applied at the end of the structure is 50. So I actually know that I have a positive value of 50 here. Okay, so I'm able to deduce what the shape of that bending moment diagram is qualitatively simply by looking at the shear force diagram and using this expression, what that expression tells me. So let's just walk our way through that one more time. Well, we know that the straight line in the shear force diagram between A and D tells me that the bending moment diagram will be an inclined straight line. By the time I get to D and I move to the right of D, the shear force has changed from a positive value to a negative value, and that means the slope of the bending moment diagram will also have changed from a positive to a negative. And so I know I have another inclined straight line, but it's going to slope in the opposite direction, which is up in this case. To the right of E, so between E and B, the shear force diagram is a curve. Okay, so the value is changing along that curve of the shear force, which means that the bending moment diagram, the slope of the bending moment diagram, will also be changing, and that means that I have a curved bending moment diagram. Okay, so if the slope is constantly changing, that by definition is a curve. So I know it's going to curve all the way up. Now, incidentally, it's important to point out that between E and B, the shear force diagram never passes through zero between E and B. So there's no local maximum or minimum in the bending moment diagram between E and B. Okay, so it's going to constantly curve upwards like so. Now, to the left of B and the right of B, the shear force changes from a negative to a positive, and that means that the value of the slope of the bending moment diagram also changes, which is what's telling me that I have a peak here and the slope changes from an upward slope to a downward slope because the magnitude of the shear force went from a negative to a positive. So again, the inclined straight line here tells me my bending moment diagram is again still a curve, but it's curving down now towards a value of 50 because I know I have an external moment applied of 50 kilonewton meters. So all that remains to do at this stage is to do discrete cuts where I need to determine what the magnitude of the bending moment is. So what I'm going to do is do a cut here because I want to know what the magnitude of the moment is there. So we'll call that cut 1, 1. We'd like to know what the value is here at the end of the straight line portion. Let's call that 2, 2. And we'd also like to know what the value is at this peak here. So let's call that 3, 3. If I know those discrete values of the internal bending moment, that's sufficient to fully define this diagram because I know what the bending moment diagram is doing between those discrete points. So let's crack on here and work out what cut 1 is. Okay, so what have I got? Minus MD, pretty straightforward, plus 67, taking moments about point D here obviously, plus 67 times the lever arm of 3 must equal 0. And so MD is equal to 201 kilonewton meters, with tension being on the bottom face. Okay. So essentially the positive number here is telling me that the direction I drew my moment in was correct. And if I was to apply that moment to the end of a cantilever, what would it do? It will bend the cantilever up like so, which indicates tension on the bottom, or would induce tension on the bottom rather. And that's what's allowing me to say tension on the bottom here. Okay, let's jump straight into cut 2. Right, what have we got? M minus ME plus 67 times 5 minus 90 times 2 equal to 0. And so ME is equal to 155 kilonewton meters. Again, positive indicating my assumed direction was correct, which would induce tension on the bottom of the structure. Okay, so then the final thing to do is cut 3. So what do we have? Minus MB plus the 50 kilonewton meter moment plus 4.44. acting over 4 meters, half because it's triangle and it has a lever arm of 4 over 3, which is all equal to 0. And so MB is equal to 61.84 kilonewton meters. Excellent. And again, assumed direction is correct, and that assumed direction would induce tension on the top of the structure. Okay, so we can just go ahead and put those numbers back onto our structure. So we had the moment here was going to have a value of 201. The moment at the end of the straight line portion, let's get rid of these dashed lines, they're kind of confusing. Don't need those anymore. So the moment here at the end of the straight line portion was 155. 155. And then the moment at the third cut had a value of minus, remember it's a hogging moment inducing tension on the top, so it's negative, minus 61.84 kilonewton meters. So that fully defines our bending moment diagram. Key points here really are, the key stages to this analysis were, first of all, get your reactions. That's what you got to do at the start of any question like this. Then we looked at the structure and we traced the loads across the structure. So we relied on this first equation, dV dx equal to minus q, which essentially says that the slope of the shear force diagram at any point is equal to the negative of the load intensity at that point. Okay, so what that told us was essentially how the loads applied to the structure transferred into a shear force diagram or produced a shear force diagram. So we traced the loads across the structure. And then we moved on and we tried to build a qualitative bending moment diagram. So we used this second equation, okay, dm dx equal to v, which simply says that the slope of the bending moment diagram is equal to the value of the shear force at a point. So we used that expression to build a qualitative bending moment diagram. And once we had a qualitative bending moment diagram, we went into the structure and made cuts to reveal the magnitude of the internal bending moment at discrete points in our structure where we needed to determine a value in order to fully define the bending moment diagram. And for the rest of the examples in this short course, we're going to follow the exact same procedure. Reactions, we're going to then follow the loads to determine a shear force diagram. We'll then build a qualitative bending moment diagram, and then we'll confirm our bending moment diagram by making discrete cuts in the structure at various points. Okay, so we'll leave it there and get set up for the next one.